Hello everyone, my name is Ahmed Radwan and I'm here to talk to you about a basic understanding of neuroimaging data, formats, terminology, nomenclature, scripting, and GUIs. I'm a radiologist by background, and I did my PhD in biomedical sciences, focusing on neuroimaging of patients who need brain surgery, where we were looking at the pre-surgical brain mapping both functionally and structurally. I worked at the KU Leuven, Department of Imaging and Pathology, Translational MRI. To begin with, I wanted to show you a quick overview of what we will be discussing. Here you can see that we'll start with a quick introduction, a dive into basic concepts and terminology. Then we will come to the role of neuroimaging in epilepsy, the types of neuroimaging modalities you might want to use, nomenclature, imaging formats and conversion, and finally we come to analysis environments and tools. So, what is epilepsy? I'm not going to go into the details of what the disease is, but I'm just going to give a high-level picture, a very basic definition, which is that epilepsy is a disorder of the brain where patients have seizures, typically more than twice. And a seizure is typically a short-lasting change in the normal electrical activity of the brain. This can be generalized or focal. Generalized means that it gets conducted all over the brain and kind of disrupts the function of the whole brain, whereas focal stays where it originates and does not disrupt functions that are far away spatially from where the epilepsy, the focal seizures happen. This can manifest clinically in different ways. Probably the most famous or commonly encountered form of that is tonic-clonic seizure, where the typical picture is a patient falling to the ground, starting to shake violently with all the muscles of the body contracting and relaxing and so on, and maybe some foaming at the mouth and a loss of consciousness. Now, as we've covered like very basic concepts of epilepsy and seizures, now we come to the focus of the talk, which is the basic understanding of neuroimaging data. In a sense, the images you get from a clinical scanner or a medical scanner device are not so different from the images you have on your computer that you can edit in Photoshop or put as your background on the desktop, or even as your profile picture on social media. All images will have image data and metadata. Metadata is what we call the header, and this encodes some descriptive information about the image file and maybe the image itself as well. So over here you can see the size of the image expressed in the number of pixels, also its DPI, its file size, the date of creation and modification, and some information about the color scheme used in the image. And here you can see an example of the image itself, but the image itself is not stored on the computer in this way. It is actually a big table that includes as many elements or cells within it as there are elements in this picture. Each of them has a certain numerical value, and this is translated to an image using the header information or other back-end info, other info that you do not see visually. So, other components of the digital image. Basically, a two-dimensional image, such as the one you see here, if you zoom in on it a lot, you can actually see the building blocks of this image, which is what we call pixels, short for picture element. And I've highlighted one of them here in yellow. Now, this is a two-dimensional image. As I said, it has two axes, antero-posterior and right to left. But if you acquire a three-dimensional image, then the elements that build up this image are not called pixels anymore, but voxels. The table I described earlier that has these, that encodes these numerical values that make up the image is called a matrix. And this matrix can have dimensions. And it relates also to the resolution, which is actually, the resolution is actually kind of a function of both the size of the matrix and the size of the voxel. So if you have smaller voxels and the matrix stays stable, unchanged, then you have a high resolution. If the voxel gets bigger, then you have a lower resolution. So these three are really interrelated. And then the color map is basically how you choose or how you inform the machine to express the intensity. So here we have a grayscale color map. So my higher intensities are expressed in a more white color, and the darker intensities are expressed in a more dark gray black color. Whereas here we have a red to yellow color map. So darker intensities are expressed in a darker red, higher intensities are expressed in yellow. Another important aspect of an image is its brightness and its contrast. If you've passed by the radiology department, if you've worked on a CT scanner or with X-ray, for example, then you probably have heard this phrase window level and window width before. But these are actually not so different from brightness and contrast, respectively. To change the brightness of an image or the window level, I would need to use this middle dial and move it up or down. And that is basically telling my software that this is my middle of the intensities, and anything above it should be brighter, anything below it should be darker. Whereas the contrast or the window width is controlled by these two dials here. So the maximum and minimum intensities that I include in my spectrum. And the tighter that or the narrower that I make this range, the flatter my image might become, or the more contrasty it becomes. So if it has a very high contrast, then typically you cannot see in full detail the spread of intensities, but it just goes from white to black, for example. So I've made a couple of examples for you here. On the left, you can see an image that, it's a copy of the one that I showed you on the previous slides over here, but I just moved this middle dial more towards the maximum range of the spectrum. And of course, this made the image much darker. Now, this image I created by making the top and bottom dials much closer to the middle dial. So I basically made my spread of intensities much narrower. And as a result of that, you can see that the brain becomes much flatter. There is no continuous spread between gray or black and white, but most of the brain is now white. And this also affects the color map, as you can see here. Another important aspect of an image is how sharp or smooth it is. So the image that you see on the right-hand side here is smoothed. That is to say that it's a bit blurry, and as a result of that, there are some structures that you might not be able to see very well. For example, over here you cannot tell the detail of what's going on here in this part of the brain, whereas on this sharp image, you can tell maybe even a bit too much, so it might be considered too noisy, that there are actually 3 structures in this area. You can also appreciate the boundaries between the fMRI cluster here and the underlying T1 much better than you can on the smooth image. So what is the role of neuroimaging in epilepsy? Well, as we know, epilepsy is a disorder of the brain. So our main focus, our most fundamental initial role as neuroimaging experts or medical personnel is diagnosis. So this patient has epilepsy, but what is causing it? This is here a coronal T2 image acquired from an MRI, and you can see clearly that there is a pathology in a certain place in the brain. The second role we need to do as neuroimagers is to localize this pathology. So where is it? In this case, we know it's in the right inferior temporal lobe. Another potential role is longitudinal monitoring and follow-up. So if this patient was not getting operated, for example, he or she will be getting medical treatment, then maybe their neurologist or neurosurgeon wants to follow up how their disease will progress. Another potential role is planning of treatment. So imagine if this patient was going to get operated surgically, the surgeons would want to know before operating how to approach this pathology, what to excise exactly, and so on. And this is something where neuroimaging can really play a key role. What types of neuroimaging modalities might be useful in epilepsy? First one here on the left is computed tomography, CT for short. And this is actually not so handy for differentiating soft tissue of different types. So here you can see that the contrast between the gray matter and the white matter is not so clear. It's not so obvious where the edge between the two is. And what you can spot quite clearly, though, is that there's something abnormal in this left side of the frontal lobe here, or the insula. Yeah? So CT is really very useful because it's quite fast. It's really useful in the emergency setting. The patient doesn't have to lie in the scanner for very long, and it is quite sensitive to calcifications and bleeding. Comparatively, MRI, which takes a longer time to acquire and requires a more cooperative, more patient or more stable patient. This is short for magnetic resonance imaging, and as you can see off the bat, it gives you a much nicer differentiation between the different types of soft tissue in your image. So you can see the outline between the gray and white matter so nicely here, as opposed to the CT image. But you can also appreciate the pathology, which is a different pathology in this case. This is a sagittal T2 image, and you can also see the boundary between the abnormal tissue and the healthy tissue just underneath. Now, these two modalities are typically used for structural investigations for epilepsy, but MRI is kind of special case because it can give you both structural and functional information depending on the contrast you use. Two other modalities that rely on, they have a very different concept driving them, is single photon emission computed tomography and positron emission tomography. Those two come from the world of nuclear imaging. So they rely on radioactive tracer that is injected intravenously and used to construct an image. In SPECT, the tracer that is injected typically decays by emitting gamma rays. And these gamma rays are detected by the scanner and used to reconstruct an image. Whereas for PET, which is short for positron emission tomography, the tracer you inject is decaying by emitting positrons. Positrons are antimatter counterparts of electrons. And when a positron and electron meet each other, they annihilate and release a huge burst of gamma energy at a specific orientation in space that is detected by the PET detector and used to reconstruct an image. Both of these images do not show a pathology. I just wanted to give you an example of both of them. And this one is actually a PET scan that is superimposed on CT. So that's another important aspect here. Both SPECT and PET do not give you a good anatomical resolution. You cannot easily tell where the thalamus starts and ends here, as opposed to MRI, where you can nicely see the boundaries between the tissues. So it is common practice to overlay the functional maps that you get from SPECT and PET on top of a T1 or a CT image to have both the structural and functional information. Now we come to the nomenclature section. And I just wanted to introduce you to some basic concepts. So CLI is probably an abbreviation you have met out there. And this is short for command line interface. And this is an interface on your machine that you use written commands in. So you type up instructions that tell the machine what to do. And a command is just a text instruction to the machine. As opposed to a graphical user interface, which is what you see here on the right, where instead of typing up instructions to the machine, you're clicking on buttons and entering maybe a couple of lines or selecting a file and then clicking go for it to do a certain task. Now, to access a CLI is actually very easy. If you have a Mac, iMac or MacBook or a Linux operating system, you just need to open terminal. On Windows, I think you can go for a PowerShell or CMD. And there you can enter a command, for example, cd space .. will take me now, if I enter it in this terminal, to the tilde, which is my home directory instead of desktop. The same kind of thing you can do in the graphical user interface, which in Windows is your Windows Explorer, or in Mac is your Finder. If you click the up button, that would take you to the directory above. What is a script? You've probably heard this phrase before. A script is basically a file that contains in textual format a number of instructions that are put after each other in sequence and executed as such. This basically tells the machine to execute a number of steps after each other to get one task done or multiple tasks done in a row. So you can have a script that automatically cleans up your data if you have a structural image required, does denoising, for example, removes the voxels of the face, and so on, all in sequence. It is very handy if you want to automate an analysis pipeline. What is an IDE? An IDE is an integrated development environment. A good example of this is RStudio, which is an IDE for the language R. And over here, you can see that the IDE is a bit of a hybrid between a GUI and a CLI. So here, this is the GUI because it is graphical. You can click on buttons and so on. But you also have a CLI, so command line interface, down here on the bottom left, where you can enter commands to do certain tasks. You can also visualize plots, see the variables that you have defined in your environment, and so on. Another variation on this theme is what is called a visual programming environment. A good example of this is a program called Mavis Lab. And Mavis Lab allows you to basically write a whole script without programming yourself. So these little blocks that you see here, they are called modules. And these modules, they contain certain blocks of code for specific tasks. You can put them in sequence. So this module here, for example, will be getting the input and then propagating it to the next layer, which does a certain task, pushes it to the next module, which does another task, and so on. And then you have one last module that gives you an output image or an output text file or something. What is a front end and what is a back end? So a front end is the part of a program that faces the user. In this case, the Mavis Lab IDE is the front end. The back end is the code that is being executed underneath the modules. So the code contained within each of these blocks, that is the back end. The back end is, for example, in the world of web development, it's what happens on the server once you click a button on the website. It is the part of the program that you do not see as a user. And now we come to imaging formats. So the most famous imaging format out there, you've probably heard of it, is DICOM. And DICOM is short for Digital Imaging and Communications in Medicine. DICOM images can be generated in classic or enhanced DICOM. And the difference between that is classical DICOM typically will have one image, one file saved per slice of your acquisition, whereas enhanced DICOM tries to combine all the slices into one file. DICOM images can be compressed or non-compressed, just like any other image out there. DICOM supports JPEG compression, but most likely the DICOM images you will be working on will have a lossless compression, because especially in the world of medical imaging, you don't want to lose any data from your image. DICOM images typically have an extension of .dcm, .dicom, or .ima, depending on the vendor you use to acquire the data. And just like other images out there, DICOMs also have a header. And the DICOM standard tries to standardize the information stored in the header and the way that the images are saved on your disk. So you can see that instead of just having the date modified and resolution and so on, here we have a whole number of different DICOM fields. That's what you see here on the left. These are the number, the code of a DICOM field. And then over here you have the content. So this is the sequence variant. This here is the MR acquisition type. It's a 3D, not a 2D. Here I can see the slice thickness, which is 0.9. My repetition time, so the TR used to acquire this image from the MRI. And down here you can see the name of the protocol on the scanner. DICOM headers differ depending on the modality, but also different vendors have slightly differing interpretations of the DICOM header. And as such, while it tries to standardize the way that medical images are produced and processed and saved, it hasn't really managed to standardize everything, at least not yet. So if you acquire data from a CT scanner or a PET scanner or an MR, and you export it to a flash disk or a USB disk and open it on your MacBook, for example, then you can see here that indeed, as I mentioned earlier, if it's in classic DICOM, we have one file per slice. This was a 3D T1 scan that had 200 slices. And as you can see, I have 200 files. This is not the most practical approach, especially if you're going to be processing this data. And that is why multiple different research formats have been developed over the years. Probably the earliest of them was Analyze, which has two files, one IMG that encodes the image itself, and then one HDR file, which encodes the header information. And then the Neuroimaging Informatics Technology Initiative created the NIFTY-1 format, which is quite similar to Analyze, except it can also have NII, and the header is slightly different. And then the NIFTY-2 format came along. That actually got rid of the separation of header and image, but encodes both of them in the same file. The difference between these and DICOM is that DICOM has a much more extensive header, whereas the header of an analyzed NIFTY1 and NIFTY2 is quite truncated. Then we have MIF, which is short for medical image format. This is a format that is used by MR-Trix, which is specifically focusing on diffusion image analysis. So mostly MRI diffusion images. Then you have .ngz and .ngh, which are formats used by FreeSurfer. And then you have NRRD, developed by the University of Utah, and MAT, which is a MATLAB format for saving data that you can also use for saving images. This is just a small selection of the formats out there. There are many others. So what do you use to convert data from DICOM to NIFTY or any other format? Well, most of these programming or image processing packages that you download that have their own formats, such as FreeSurfer or MR-Trix, will have tools to allow you to convert the data from DICOM to their format. But if you're going to be using NIFTY, you have a good example of this, which is MRI-Cron or MRI-Cro GL, that gives you both a CLI and a GUI. Over here, you can see an example, just a snapshot of the GUI of MRI-Cro GL, which is open access. You can just download it for free. And if you click on import, you can here, as you can see, convert DICOM to NIFTY. With MR-Trix 3, you have this command called mrconvert, which is very handy and quite powerful and can convert to NII or MIF or I think MGZ as well. However, it is only a command line tool. FreeSurfer offers the MRI_convert command, also only a command line tool. And there are many others out there. A good note to keep in mind is that you always need to check your output, because sometimes the DICOM to NIFTY conversion can go very wrong. So you need to be able to spot what went wrong or what went well and what to try and fix. Also, there is quite a bit of support out there online for you to be able to ask for some help if something goes wrong and you don't know how to fix it. Analysis environments and tools. If you're working in a research setting, most likely you've already encountered something like Shell, Python, MATLAB, Octave, and R. R has made a good name for itself in the world of statistical analysis, but you can also use it for creating a script or analyzing a functional data set. It has libraries for FSL, I think, now, and ANTS, and so on. Octave is a free alternative that was developed to kind of address the shortcomings of MATLAB. So MATLAB is a commercial program that is developed by MathWorks. It is very popular in the research setting for many different applications. However, it is not free. That's where Octave comes in. So Octave is basically a free alternative developed by the GNU community to kind of replace MATLAB whenever possible. Python is an open access, open source programming language that is very, very popular these days. It has many different libraries that allow you to do diffusion analysis, fMRI analysis, morphometry analysis. Depending on whatever modality you're working on, you probably most likely will find a library for it in Python. It also has a huge base of supporters and a very active community, both in development and user support. Shell is an interface platform that you can use to instruct your machine what to do. If you have Linux or Mac operating systems, it's not strictly a programming language, but more of an instructional platform that has many different flavors. ZSH, I think, is the most recently developed one. I think Bash is the most popular out there. And these are all scripting languages that you can use to construct your own script and automate a whole analysis pipeline. Over here, you can see an example of Shell. So this is actually talking about what you need to change if you started working in Bash and now you want to shift to ZSH. Here you can see examples of analysis environments and tools. There are many different ones out there. I'm just listing the most popular ones, the ones that I know about and have used in the past. This here is SPM. Here is FSL. These two kind of focus on fMRI. I think they started focusing in the beginning on only fMRI, but for example, FSL has expanded to the world of diffusion imaging, morphometric analysis, and SPM has also expanded into morphometric analysis, but I don't think so much into diffusion, both of which also offer group-level statistical packages that you can use to compare groups and calculate group-level statistics. And then you have the advanced normalization tools, which is a very powerful toolbox for registration, brain extraction, and so on. MRTrix is focusing on diffusion imaging, but you can also use it for other modalities if the concepts or the steps that you want to apply are not so different. And then you have 3D Slicer, NiftyReg, and Explore BTI. All of these are research packages, that is to say that they are not specifically FDA or CE approved. So typically you cannot use them in the clinical setting. And on the flip side, you have clinical tools which were developed by commercial entities such as Philips, GE, Siemens, Toshiba, etc. These will typically have an FDA-approved mark and also CE approval that allows you to use them in the clinical setting, both in the States and in Europe. I'm listing here some examples, but I'm not going to go into details about that. Thank you very much. This has been just a quick crash course into the basic understanding of neuroimaging data. Please feel free to send me an email or with questions, or if you would like to discuss something specific. This is my email here. I have no financial disclosures or conflicts of interest to disclose.